Okay, so we'd like to welcome Jinfeng Liu, and he is going to be talking to us about a moving horizon estimation for nonlinear systems. So I'll turn the time over to him.
Thank you. Good morning, everyone. I'm Jinfeng Liu from University of Alberta. Today I'm going to talk about our work on robust moving horizon state estimation for nonlinear systems. The motivation of this work is essentially from output feedback control systems. As we know, most of modern control systems are designed based on state feedback. However, in many applications, not all the state variables are measured. So we only have output measurements. And state estimation provides a way to reconstruct the state of a system. For linear systems, there are standard solutions to state estimation. There are Nuremberg observers and Kalman filters. However, state estimation for nonlinear systems is much more challenging. One approach is to linearize the nonlinear system successfully at each sampling time, and then apply the linear solutions to the linearized model. For example, extended Kalman filters and extended Nuremberg observers. Actually, these designs are widely used in the industry, especially extended Kalman filters. However, this approach is an ad hoc solution to nonlinear systems. A more favorable approach is to design observers or estimators, explicitly taking into account nonlinearities of the system. For observers or estimators that explicitly accounts for nonlinearities, we can broadly classify the results into two categories. In the first category, the design of the observers, disturbances and measurement noise are not considered explicit, and we can say this kind of design is deterministic approaches. And in the second category, the information of disturbances and measurement noise are taken into account explicitly. One example is moving horizon state estimation. I'm going to talk about these approaches a little bit in the following slides. Let's first focus on deterministic nonlinear observers, and we consider a general nonlinear system that can be described by these equations. In this system, X is a system state, Y is the output, and the omega is process disturbance, V is the measurement noise. As just mentioned, in the design of deterministic nonlinear observers, the information on the process disturbance and measurement noise is not used. And the observer in general is a function of the state of the observer itself and the output measurements. And a common form of this design F includes two parts. The first part is a copy of the nominal system model. And in the second part, it is based on the measured output and the predicted output. Also, it includes a gain term. This form is actually very similar to the design of Nuremberg observers. But the key difference in this kind of design is in the gain. The gain for nonlinear systems in general is time varying. However, but in the linear case, the gain is constant. This kind of design, deterministic nonlinear observers, has some properties. For example, we can characterize the effects of bounded disturbances and noise. Also, it has tunable convergence rate, for example, by tuning the observer gain. Moving horizon estimation is an online optimization-based approach. It uses a model of the system as well as the information on the distribution and boundedness on the disturbance, noise, and the system state. It uses the most recent several measurements within a finite estimation window. All the measurements the information provided by the measurements outside this window are summarized in a term called arrival cost. And this arrival cost is actually used in the cost function. If the arrival cost is approximated accurately, then we can actually show the convergence of the estimates given by the moving horizon estimation to the actual system state. However, for constrained nonlinear systems, the approximation of the arrival cost is not an easy task. As just mentioned, deterministic observers and moving horizon estimation, they have their advantages and disadvantages. If we list their properties and compare them, we can see deterministic observers, you see, they do not consider uncertainties explicitly, but in moving horizon estimation, uncertainties are considered explicitly. And deterministic observers is not optimal, but moving horizon estimation, I would say MHE is optimal. And deterministic observers has tunable convergence rate, but the convergence rate for moving horizon estimation is unknown. Because deterministic observers have tunable convergence rate, so we may have separation principles in the design of output feedback control systems. This is actually very important from an output feedback control point of view. But for moving horizon estimation, because the convergence rate is unknown, so in general, separation principle is not available. And moving horizon estimation is robust to measurement noise, but deterministic observers is could be very sensitive to measurement noise. But if we have bounded uncertainties in the framework of deterministic observer, we may be able to characterize the robustness of this observer to the bounded uncertainties. But in moving horizon estimation framework, this is very difficult. Also, for deterministic observers, it uses only the current measurements. So we don't have to estimate the arrival cost. But in moving horizon estimation, it depends actually on all the past measurements. That's why we need the arrival cost. From this list, we see that both has some very desirable properties, but at the same time some drawbacks. So can we combine the advantages of the deterministic observer and moving horizon estimation into a unified framework? That's the primary objective of this work. And we propose a robust moving horizon estimation for nonlinear systems with bounded uncertainties. And in this design, we try to combine these advantages. We consider nonlinear systems that can be described by these equations. I showed them before. And the basic assumption is that F and H are locally Lipschitz. And also, we have bounded process disturbance measurement noise. And we assume the measurement Y is sampled every sampling time, delta. One fundamental assumption in this work is that we assume we can find a nonlinear deterministic observer for this system, and this observer is able to track the actual system state for the nominal system. Also, this observer is locally Lipschitz. As mentioned before, for deterministic observers, if we have bounded uncertainties, we could characterize the effects of these bounded uncertainties, for example, bounded process disturbance and bounded measurement noise. So if the deterministic observer gives us an estimate, we know the actual system state is within a bound like this. And this bound can be approximated. So can we use this bounded boundedness information in the design of moving horizon estimation. If we look at this equation, this kind of relationship, we found this boundedness information cannot be applied directly. Why? That's because it has dependency on x. X is the actual system state. But fortunately, we can use this bound indirectly. That is to use the output measurement and the predicted output measurement, predicted output. Based on the difference between them, we can say when the difference between the actual output and the predicted output is small, then the estimate given by the deterministic observer should be very close to the actual system state. If the difference between the two is very large, then the accuracy or the reliability of the estimate given by the deterministic observer is not so good. And this slide shows the detailed design of the proposed robust moving horizon estimation. In this design, we have the standard constraints in the design. Also, we use arrival cost, but we have some new constraints. In these constraints, basically we use the deterministic observer and the previous measurement to generate a reference, state reference or estimate, and then based on this state estimate and measured output, current output, we generate a confidence region for the current estimate. And the estimate of this moving horizon estimation is only allowed to be optimized within this confidence region. In this constraint, the parameter kappa is an important parameter. It determines the size of the confidence region, and the confidence region at different time instance could be the sizes could be different. Under certain conditions, we can actually prove the estimation error given by the proposed moving horizon estimation is a decreasing sequence, and the estimation error eventually bounded by will be bounded in a small region. This constraint, this condition, essentially requires the sampling time should be small enough, and also the bounds on the uncertainties should be sufficiently small. The proposed moving horizon estimation combines the advantages of deterministic observers and moving horizon estimation in a unified framework. And we can get bounded estimation errors for bounded uncertainties. This is very difficult to achieve in the classical moving horizon estimation scheme. Also, it has reduced sensitivity to the accuracy of the arrival cost. Why? Because we use deterministic observer to calculate the confidence region, and this confidence region can actually give us additional information, so we can count less on the arrival cost. It has provable and tunable convergence rate. This is actually very important from an output feedback control point of view, which means we may have effective separation principles in the design of output feedback control system based on moving horizon estimation. If we use sample data observers, then we can actually reduce the requirement on the size of the sampling time, so we can use relatively large sampling time. As mentioned, the design parameter kappa is very important. When kappa is chosen, for example, approach is 0, then the proposed robust moving horizon estimation will reduce to the deterministic observer. And when kappa is too large, then the robust moving horizon estimation will become the regular moving horizon estimation. We have applied the proposed design to a chemical process, a CSTR. The example is used in a similar example has been used in the previous talk. In this example, we have two states. One is temperature, one is the concentration of the product. And we assume the temperature is measured, but we need to estimate the state of the entire system, includes Ca and T. Here. And we consider bounded uncertainties in the process, in the measurement noise and process disturbances. We designed a reduced order deterministic observer for the concentration. This observer is actually a copy of the second equation without considering the disturbances. And the design parameter kappa is tuned to be 0.02. In this slide, we show the results when we compare the deterministic observer, the classical moving horizon estimation, and the proposed moving horizon estimation. This plot shows the state trajectory. This is the temperature trajectories. This is the concentration trajectories. The black lines correspond to the proposed moving horizon estimation, and the red lines correspond to the classical moving horizon estimation. And this plot shows the normalized estimation error of these different schemes. From this plot, we can see the proposed moving horizon estimation gives the smallest normalized estimation error. From these plots, we can actually see the fluctuation of the proposed moving horizon estimation is relatively smaller compared with the classical moving horizon estimation. We have also compared the proposed moving horizon with the classical moving horizon estimation and the deterministic observer from a performance point of view based on a performance index and showing this equation. This performance index is basically a weighted estimation error. From the simulation results, what we found is that in all of the simulation runs, the proposed moving horizon estimation gives the best performance, the smallest performance index, which is the smallest weighted estimation error. We have also studied the effect of the length of moving of the moving horizon estimation schemes. Basically, we carry out simulations with different horizons. From this plot, what we can see is that the proposed moving horizon estimation has relatively small dependency on the size of the horizon. When the horizon is small, it gives much better performance compared to the traditional moving horizon estimation. As the horizon increases, the two approaches eventually will converge to the same performance. But from this simulation, we can see much smaller horizon can be used in the proposed moving horizon estimation. So in conclusions, in this work we discussed a robust moving horizon estimation scheme for nonlinear systems with bounded uncertainties. And it can combine the advantages of deterministic observers and also moving horizon estimation in a unified framework. The key feature is that this moving horizon estimation uses confidence regions provided by the deterministic observer to estimate state estimates. As discussed, it maintains the optimality from classical moving horizon estimation. It has tunable convergence rate. I didn't show it here, but this can be proved. So we could have potential effective separation principles in the design of output feedback control systems. The confidence regions provides another approach for the arrival cost error compensation in addition to traditional approximation of variable cost. So thank you for your attention. I would like to take your questions.
We have time for 1 or 2 questions.
Did you assume any plant model mismatch in your simulation?
In the model, actually, we consider the process disturbance. There's some random values added to the model, and the model used in the design of the observers, it doesn't know the disturbance, but in the moving horizon, it knows the distribution and the bounds of the uncertainties.
Great. Okay, great. Let's thank Jinfeng one more time.